Today's lesson is a revision of the theory behind work, energy and power, and this section is very closely linked to the previous section that we've done, which is on mechanics. So it starts out just with a reminder of two very important diagrams that we're required to draw. Those are free body diagrams and force vector diagrams. So a couple of components or a couple of elements that must always be present. Firstly, the object is always represented by a dot. That dot represents the center of mass of that object, and strictly speaking it must be a dot. It cannot even just be a circle. It is a dot that represents the center of mass of that object. The second thing is that all forces must be directed away from that object. So if we have an example of somebody pushing a box up a slope, then we can see that they are pushing the box and applying the force on the back of that box, which means that you would be tempted to draw your free body diagram with an arrow pointing onto that object, which would be wrong because all forces must originate on that object. So you would show that force as originating on the object and clearly label it as the applied force. The normal force we know is always perpendicular to the surface that the object is on. The force of gravity is always the force that acts vertically downwards, and then there might be a frictional force which would act parallel to the slope and opposite to motion. A common mistake is that we would include the components of the gravitational force, those being Fg perpendicular and Fg parallel. Now, either one or the other is allowed or is possible. You can either show the two components of the gravitational force, Fg perpendicular and Fg parallel, or you can show only the gravitational force. You cannot show both of them together because drawing it like this implies that there are actually three forces acting on that object, where it is only the one gravitational force acting on the object. Something else that's important for a free body diagram is that there must always be a key drawn on the right hand side, where you just say here Fa is the applied force, Fg is the force of gravity, etc. It is just to make sure that the person marking your script knows what each symbol means. A slightly less common diagram that's required is called a force vector diagram. This is where the object is represented by a box or a simple shape, and the main difference here is that we show where the force is acting on the object. So for example, the gravitational force acts from the center of mass of that object. The normal force acts on the bottom surface of that object. The applied force is acting from behind onto the back of that object, and the frictional force acts along the bottom surface. So once again, this is not a very common type of diagram to come up, but it is one that you can be asked. And the only difference here is that you have a box representing the diagram and that you show exactly where that force acts on the object. So, as we said, this is closely linked to mechanics, and so once we have an understanding for these basic diagrams, we get to defining the new concept, and that is the concept of scientific work. Now, I'm specifically calling this scientific work because it can be quite confusing that we think when we say work, we tend to think that studying for a test is work, or trying to lift a weight is work, or trying to push an object is work. Where scientifically, there's a very strict definition for what is required in order for work to be done. Definition given there, the definition basically explained by this formula here, says that work is done when a force is applied on an object and that object moves in the direction of the force. So that's why I've taken a lot of time here to specify that scientific work is only done when a force is applied and the object moves in the direction of the force. So a couple of examples of where we would think that work is being done, where scientifically that is not true. The first one is somebody attempting to push an object. Somebody that is applying a big force on the object, so there is an applied force, but because of the static friction between that object and the ground, the object does not move. So we would, in everyday life, we would call this work because they are exerting energy, they are expending energy, it is tiring. But scientifically, this is not work because there is a force applied but the distance that this object has moved is 0, and therefore 0 work has been done. The second example of where we commonly think work is being done when it is not is when somebody is carrying a box across the floor. So they've lifted it up and they now move at a distance of, say, 10 meters. Now we're tempted to think here that work is being done because they have applied a force and they have moved the object. But scientifically, once again, what we need to see is that in order to lift this box, this person must be applying a force upwards. They're applying a force upwards, and the displacement is to the right, which means that the angle between force and displacement is 90 degrees. And so by using this formula here, we can see that cosine or cos of 90 is 0. So this applied force is not doing any work on the object because the force and the direction of motion are perpendicular to each other. So those are two common examples of where we think that we are doing work, where we are not necessarily doing work. Some simpler examples where, for example, a car, we'll call it an ambulance, applies a force with its engine, the applied force of 50 newtons, and it drives, say, 10 meters. Right, so here we can start out by saying that we can see that the applied force and the direction of motion are in the same direction. Therefore, this is going to be scientific work. So our work done is then the applied force of 50 newtons multiplied by the displacement of 10 multiplied by the cosine of the angle between them. If both are in the same direction, that means the angle between them is 0 degrees, and cos of 0 is 1. And so we can say that the work done by this force is then 500 joules. So work should be seen as a form of energy, which is why it has the unit joules. And the main reason why this is important is because we need to start seeing work as a way of transferring energy from one object to another. So what's important to see here is that work is a scalar quantity. Although it is the product of two vectors, because it is the dot product and we're using the cosine here, we say that this product of two vectors gives us a scalar quantity. The reason why this is important is because later on when we start looking at, for example, a force of friction of 2 newtons that applies in the opposite direction, and we now say that the work done by friction is equal to that frictional force times the displacement cos theta, where here the friction force is 2, the displacement is still 10 meters, but now the angle between the displacement and friction is 180 degrees. Because it's 180 degrees, cos of 180 is negative 1, which means that the amount of work done by friction is negative 20 joules. Now it's important to see work here as a scalar quantity, because when work is seen as a scalar quantity, we see this 500 joules as 500 joules of energy is added to the system. Right? Because in order to move this car 10 meters that way, you need to add energy to that system. A negative work then does not mean work in the negative direction. What it means is that energy is removed from the system, right? Which is what we know friction does. As the object attempts or tries to move in a certain direction, friction is what slows it down and steals that energy from us. Right, so important here, and a common question to come up is something along the lines of what does it mean when we say that 1,000 joules of work is done? What it means is that 1,000 joules of energy was added to the system, right? In the same way as negative 300 joules of work means that 300 joules of energy has been removed from the system. Just a quick note here that this does not imply that the conservation of energy doesn't exist. When we say that 20 joules of energy is removed from the system, we don't mean 20 joules of energy disappears forever. What we mean is that 20 joules of energy is lost to this vehicle, right? So it's lost in the friction between the tires and the road, it's lost in the sound that's emitted, and by lost I mean it just goes out into the universe and isn't usable to this vehicle or in this system anymore. So it is not that we are destroying energy, it's just that it's lost to any form of useful type of energy. Right, so that is work as a scalar quantity. What we then start to see is, in much the same way as we covered mechanics, where we start out by learning about individual forces and then start saying, well, these forces don't act on their own. Forces all act together on an object, and therefore it becomes important for us to define something called a network. Because in this example over here, to say that this object has only gained 500 joules or only lost 20 joules is not really giving the full story. What's important to say here is that this object has gained 500 while losing 20, so strictly speaking, this object has gained 480 joules of energy, and that is called network. So there are two ways in which network can be calculated. The first one is that we can say that the network is simply the sum of all of the works, or the sum of the work of all of the forces acting on this object. So in this case, we would say this object has two forces acting on it. This is also keeping in mind that there are, strictly speaking, four forces acting on this object. There is a force of gravity acting downward on the object. There is a normal force acting upward. But the work done by both of those forces is zero. The reason for that is that the force is acting downward and the motion is to the right, so they're perpendicular to each other. So you will see in some examples we actually write out the network is equal to the sum of all of those. It is not necessary, but you can do it, where you would then say that the work done by the applied force was 500 joules, the work done by the frictional force was negative 20, and then the work done by the other two was 0 each, which means that our network is then 480 joules. Now, another way of looking at this would be to say that the network is very simply just our same work formula for the net force. The network is equal to the net force multiplied by the displacement cos theta. And so in this case, we would see here that the net force acting on this object is 50 newtons to the right minus 2 newtons to the left. Our net force is then 48 newtons to the right. And so we can say our net force is then 48 times that displacement of 10 meters, and the angle between those two is 0, once again, 480 joules. And so either way, we see that we arrive at the same answer using our two different approaches for how to calculate the network done on an object. The reason why this is important is going back to Newton's second law, much the same as in mechanics. Most of this relates back to Newton's second law, and also in the section that we did on momentum, where you can always express momentum or change in momentum in terms of Newton's second law. The reason why this is important is because we can see that when the net work is greater than 0, or put more simply, when the net work is not equal to 0, that must mean that the net force acting on this object is not 0. When the net work acting on this object is not 0, it means that our net force is not 0, because if the net force was 0, our net work would automatically be 0. What this implies is, by Newton's second law, that the object is accelerating. Again, note here that accelerating refers not to only increasing speed, it refers to a change in speed, right? Speeding up or slowing down. And then you can finally start to see how net work is related to energy. Because when an object accelerates, when it changes its velocity, our formula for kinetic energy, 1/2 mv squared, which says that the kinetic energy of an object is half the mass of the object multiplied by the velocity squared. When the acceleration changes, the velocity changes. So when this object accelerates, its velocity changes. Because its velocity changes, its energy changes. Right? So this is a very long way of arriving at what we call the work energy theorem. There's just a reminder of what kinetic energy is, also measured in joules. Same for potential energy, which is measured as a height above the surface of the Earth. And this then gets us to the work energy theorem. The work energy theorem, which we don't need to know that whole derivation over there, the work energy theorem very simply says to us, when there is a net force acting on an object, that net force is going to do some net amount of work. Because there's a net amount of work being done on the object, that means the object is accelerating. And because that object is accelerating, that means its energy is changing. Specifically here, it's kinetic energy. And this is called the work energy theorem. So what we can do here is we can, for this object, if we knew the mass of this object, let's say it's 1,000 kilograms. For this object, we can say, well, now that I know this force, I can actually calculate the acceleration of this object. I can say, well, I can calculate the final velocity of the object, assuming that it starts from rest, because we can now say that the net work done on this object is equal to its change in kinetic energy. Net work here we calculated as 480 joules, meaning this object has gained 480 joules of energy. And so our change in mechanical energy, because the mass remains the same, it's just the change in our velocity that matters. So 1/2 times 1,000. Final velocity is our unknown here, minus the initial velocity. And so we can solve then to find that our final velocity is. So we find that the final velocity of this object is then 0.98 meters per second. Now, we're often going to see that it would be possible to solve this question the other way, where you say that since I know the net force acting on this object and I know the mass of the object, net force being 48 newtons and the mass being 1,000 newtons, I can then use that to solve for my unknown acceleration and then use an equation of motion to find the answer. The reason why you need to know both methods is because the question can often state explicitly using energy considerations or using the work energy theorem, in which case, even though you'll get exactly the same answer using equations of motion, you must answer the question using the work energy theorem. Right, so there's often confusion about our work energy theorem because, as you saw, in discussing mechanical energy, which is the total energy of an object, we said that it is the combination of kinetic energy and potential energy. Now, the potential energy of an object is dependent on the object's height above the surface of the Earth. Right? As an object gets higher up, it means that it can fall further, it has more potential to do work. Now, you can still use the work energy theorem even when an object is moving upwards or downwards. The reason why that's true is because even as it's moving upwards or downwards, whether it's sliding up a slope or up or down a slope, there is still going to be a net force acting on that object. So the work energy theorem does apply in all scenarios as long as you ensure that you are dealing with the entire net force acting on that object. Right, then we get to the conservation of mechanical energy. This is something that we covered sort of quite early on in high school, but it does become important here again, and it is the idea that in an isolated system, again, going back to the isolated system that we referred to in the momentum and impulse section, this is a system in which the net external force is 0. In an isolated system, the total amount of mechanical energy remains constant. So basically saying, when there's no friction acting on a system, the amount of energy remains constant, and the common example that we do is something along the lines of when you have an object at a certain height above the surface of the Earth, it has a certain amount of energy. As you drop that object, it starts to fall, its potential energy decreases as it gets closer to the surface, but while its potential energy decreases, its kinetic energy increases, and so the total mechanical energy remains constant. Now, why this is important here is because in specific scenarios, when you are told that it is an isolated system or that there are no external forces or the net external force is 0, you can then assume that our mechanical energy remains constant. And then you can use that to perform calculations. The simple calculations here being, if we start with a certain object 10 meters above the ground. It is a 1 kilogram object. We start with this object and we're told that it is an isolated system. We're asked to use energy considerations to calculate the velocity of this object just before it strikes the ground. Now what we can say here is we can say that change in mechanical energy is equal to 0, meaning no energy is gained or lost, which means that the initial kinetic energy plus the initial potential energy minus the final, that is the final kinetic final potential minus the initial kinetic and initial potential must be equal to 0. And then we can say for this object, the initial potential energy is 0 because, oh, that's not true. The initial potential, wow. Guys made me so nervous. The initial kinetic energy, because this object is released from rest, the initial kinetic energy for this object is 0. When this object strikes the ground, the potential is going to be 0 because it has no further to fall, so the final potential energy is then also 0. So we're left with EKF minus EPI is equal to 0, and then we can solve that using EKF is equal to EPI, and we can solve for our unknown. Again, this is only possible when the mechanical energy is conserved, meaning there are no external forces that are changing the energy of the system. So what becomes important at this point is to define or to distinguish between the two different types of forces that exist. Those are called conservative forces and non-conservative forces. So there are 3 conservative forces. Those 3 conservative forces are the gravitational force, elastic force, and electrostatic force. Now, the gravitational force is the only conservative force that we deal with. In high school, we say the only conservative force that we are going to come across is gravity. The reason why it is conservative is because whenever we do work against gravity, meaning that in order for me to lift this object from here to here, I have to apply a force upward on that object. So what we say is I'm doing work against gravity because gravity is pushing this object down, I am pushing the object up. Now it is conservative because that energy is not lost. I expend a certain amount of energy to lift this object, but when I've lifted this object, it has now still got that energy in the form of gravitational potential energy because it can fall back down to where it started. So we say that it's conserved because when you do work against it, that energy is not lost. Right? You'll see that the definition is slightly different to that. The definition says a force for which the work done in moving an object between 2 points is independent of the path taken. Basically saying that for me to move this object upwards by 1 meter, it doesn't matter what path I take because this object has gained 1 meter of potential energy. So even if I take it in a very roundabout route and end it 1 meter above where it started, this object has only gained 1 meter of potential energy. This is in contrast to most of the forces that we deal with on a daily basis. These are known as non-conservative forces, where the definition for non-conservative force is a force for which the work done between 2 points is dependent on the path taken. Right? A common example would be if you need to push a car from one point to another. Right? If you need to push a car from point A to point B, the work that you're doing is going to be mainly work against friction between the car and the road that makes it difficult for you to move the car. Which means that if you're going to take a very roundabout route to get the car from point A to point B, you are going to have to work against friction on that entire route. So the longer the path is, the more work you have to do. So that is our big difference between conservative and non-conservative forces. Conservative forces, the path doesn't matter. What matters is where it starts and where it ends. For a non-conservative force, the path absolutely matters because you have to use energy to overcome that force every meter that you push this object. The non-conservative forces that we are going to deal with mostly are friction, tension, and the applied force. So now what becomes important here is that we understand that conservative forces, as the name suggests, means that energy is never lost. Right? When an object is lifted up or falling down, the energy doesn't change. It's converted from kinetic to potential or potential to kinetic, but the energy is not lost. Whereas when I push an object from one place to another, because I'm doing work against friction and causing some heat and sound, I'm losing that energy. That energy is lost forever, or lost to me forever. So what we find is that our conservation of mechanical energy, which we said in an isolated system, meaning mechanical energy does not change, is not true in a non-isolated system, meaning it is not true when there are non-conservative forces present. Because non-conservative forces change the energy of a system, right? Either whether it's through friction that detracts or removes energy from that system as you try to use it, or if it's an applied force that's constantly adding energy externally, right? When I'm pushing an object, that's energy that I've got from the food that I've eaten that's stored as potential energy in my muscles that eventually is able to be used to move the object, right? So whenever there's a non-conservative force acting on an object, that object energy changes. And so we can rewrite our conservation of mechanical energy to now say that the mechanical energy in a system, the change in mechanical energy in a system, is equal to the work done by the non-conservative force or forces. A common mistake here is that we tend to see, oh, friction's there, so it must be the work done by friction, whereas if there's friction and an applied force, it is the combination of those non-conservative forces. Right, and that is called the work done by a non-conservative force, where that is equal to our change in the object's kinetic and potential energy. Right, the last part of this section is a very brief overview of what power is. So the idea here is fairly simple. The idea here says that if you have one person who is capable of lifting a 100 kilogram object through a distance of 1 meter, we can say that they're doing a certain amount of work. Strictly speaking, we can say that they are applying a 980 Newton force, a distance of 1 meter, so they're doing 980 joules of work. We can then compare this to a person who lifts a 10 kilogram object 10 times. Through a height of 1 meter. So what they've done is they've done a force of 98 newtons, applied it over a distance of 1 meter, and then repeated that 10 times. And so these people have also done 980 joules of work. So scientifically, there is no difference between the work that has been done here. Lifting 100 kilograms once or 10 kilograms 10 times. There's no difference between the scientific type of work that they have done. The difference comes in mostly with the rate at which it's done, how fast that work is done. And that introduces the last concept in this section, that being power. We say that power is the rate at which work is done or energy is expended, and there's our formula: power is equal to the amount of work done divided by the time. So this is often right at the end of a question when you've already calculated the amount of work done by a specific force or on a specific object, and then they say if it takes 0.2 seconds, then calculate the power, and you just sub it into this formula and remember that the units of power are watts. The most common place where, or a common type of question here, is a question of a pump that is lifting water from a well or lifting it up into a reservoir or something to that effect. So what often gets confusing is that we are told that the pump can pump 1,000 liters per minute. And we say it's going through a height of 20 meters. The reason why this often confuses us is because liters don't really correspond to any kind of force to us. So what we are often given is we are told that 1 liter is equal to 1 kilogram. And So what you should start to see this as is that this pump can lift 1,000 kilograms in 60 seconds. And as soon as you've done that, you've solved all the problems, because lifting 1,000 kilograms means that you need a 9,800 Newton force. Because you've now got the force and you've got the displacement, you can calculate the amount of work that this pump is doing. And then because you've got the amount of time it takes to do that work, you can calculate the power that this pump has or expends.